SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Welcome to an interesting and joyful journey in analysis, particularly in sequence series, harmonic series, and logarithms. So let us start with definitions. Before I define sequence and series and harmonic series and sequence, real mathematics, the deep mathematics, the spring of mathematics started after 17th century. Before that, mathematics much or less based on the intuitive way. Geometric feeling and intuitions play major role in that. But as mathematics developed, progressed, mathematicians started doubting few things. The first thing that the usual intuitive idea that a continuous function is differentiable almost everywhere. But Weierstrass first shown and proved that you can have a continuous functions which is nowhere differentiable. And there geometric ideas, intuitive ideas failed, and there a foundation, real foundation of mathematics, deep mathematics started. And then new mathematics, modern mathematics, analysis, functional analysis, topology started in full swing. The first definition is sequence. Everybody knows a sequence is a function defined on the set of natural numbers n. So any function f from n to r means values are reals. That function is a sequence, and its nth term is called the nth term of the sequence. If we denote that by an, then the sequence an is denoted by this symbol an. And corresponding to this sequence, if we take the sum of first n terms and we define Sn as a1 plus a2 plus so on an, then we have again a sequence Sn, where Sn is a1 plus a2 plus an, and this sequence is called the series an, and Sn is called the nth partial sum of the series. Now the series and sequence may converge, may not converge. As for example, if I take an equal to 1 upon n, then as n increases, 1 upon n gets decreases. So as n tends to infinity, this tends to 0. And so we say that sequence an converges to 0. But if I take the sequence an, where an I define as, let's say, n belongs to n, then as n increases, an also increases, and this tends to infinity as n tends to infinity. So an tends to infinity as n tends to infinity, and in that case the sequence is not convergent, that is, it is divergent, because n is positive, so it diverges to plus infinity. Now if the sequence is monotonically increasing in the sense that the terms get larger and larger, so an is less than or equal to an plus 1, less than or equal to an plus 2, and so on, a1 less than or equal to a2, and so on. If this is the case, we say the sequence is monotonically increasing. And if it is other way round, say a1 is greater than or equal to a2, greater than or equal to so on, an greater than or equal to an plus 1, and so on, then we say it is monotonically decreasing sequence. Now if a sequence is monotonically increasing and is bounded from above, then it is convergent. And if the sequence is decreasing, so terms get smaller and smaller, and it is bounded from below, then also it is convergent. So a increasing sequence which is bounded from above is convergent, and a decreasing sequence which is bounded from below is convergent. And if the series is increasing and not bounded from above, and if terms are non-negative, terms are positive or non-negative, then it tends to infinity if it is not convergent, and if all terms are positive, it diverges to plus infinity. And if the series terms decreasing, monotonically decreasing, and it is not bounded from below, then it diverges, it is not convergent, and it diverges to minus infinity. So if the sequence is bounded, then if it is increasing, it is convergent. If it is decreasing, it is also convergent. So next is we define a Quasi sequence. A Quasi sequence, named after one of the finest mathematicians of modern mathematics, Quasi sequence is defined. So a sequence Sn of reals is called Quasi, if given any epsilon greater than 0. There exists n0 belongs to n such that the absolute value of the difference between Sm and Sn, this is less than epsilon for all m and n greater than or equal to n0. That is the terms of the Quasi sequence. The terms of the Quasi sequence from some point onwards, from some term onwards, get close to each other, get clustered together. And now the famous result, Quasi criterion for convergence. A sequence Sn of reals is convergent if and only if it is Quasi. So that is Quasi Criterion or criteria for convergence. So a sequence Sn of reals is convergent if and only if it is Quasi. It is Quasi, and we define the Quasi sequence. So if this is the case, then a sequence Sn of reals is convergent if and only if it is Quasi. And if I take the series sigma an, if I take the series sigma an, then following for the series sigma an, the following statements are equivalent. One is the series is convergent. 2, for every given epsilon greater than 0, there exists some n0 belongs to n such that whenever m is greater than n, greater than or equal to n0, the sum absolute value of the sum ak, k varies from n to m, is less than epsilon. And third, given epsilon and any given epsilon greater than 0, there exists n0 belongs to n such that whenever n is greater than or equal to n0, we have this difference k n to n plus p. This ak is less than epsilon for p equal to 0, 1, 2, so on. Now let me define the harmonic sequence. Harmonic sequence Sn, where Sn is defined as 1 plus 1/2 plus 1 upon 3 and so on so forth. Last term is 1 upon n. So if I define sequence Sn where Sn is 1 plus 1/2 plus 1 upon 3 plus 1 upon n, that means first n natural numbers are inverted. 1, then inverse of 2, so 1/2, reciprocal of 1, 3, so 1 upon 3 and so on. Reciprocal of n or inverse of n, 1 upon n. Now this sequence is called harmonic sequence. Now for the series, if I take the series an equal to sigma 1 upon n, then Sn is called its nth partial sum. Nth partial sum. So we'll show that this harmonic sequence Sn or this series sigma 1 upon n is not convergent. it is not convergent. In fact, we will show that as n tends to infinity, it tends to plus infinity. So, the standard way is, let us assume the contrary. We suppose that this harmonic sequence or series sigma 1 upon n is not convergent. Suppose it is not convergent, so it is convergent. So, we assume that Sn is convergent. Now, in that case, the convergent, then we must have this Quasi sequence, and limit as n tends to infinity must be a finite value. So, for every epsilon this is true. So, let me take epsilon equal to 1 upon 4 greater than 0, say. So, I take epsilon equal to 1 upon 4. Now, corresponding to this epsilon, we can find some n0 belongs to n such that, and Quasi criteria say that the sequence Sn is convergent if and only if it is Quasi. So, we are using that. So, this difference Sm minus Sn, that must be less than epsilon, and here epsilon is 1 upon 4 for all m greater than n greater than or equal to n0. Now, if Sm is 1, then 1/2, 1 upon 3, and so on. Now, m is greater than n, so first n comes. So, 1 upon n